In the last section, we talked about the idea that there were many different properties of definite integrals, or properties of areas under a curve, that we can make use of to try to either estimate the value of difficult integrals, or maybe save some work on calculating integrals that were very similar to ones that we had previously calculated. Well, in this section, we're going to take a look at another interesting property of integrals, or at least something else that we can do with a definite integral that will be of paramount importance to understanding how exactly we really might be able to kind of speed up and accelerate the process by which we evaluate them. So let's go ahead here and take a look at this opening motivation. And it's actually a really simple question. How do you compute the average of 4 numbers? This is not a trick question. It is literally that easy. How do you calculate the average of 4 numbers? Let's call these numbers A, B, C, and D. Well, this is not really difficult at all, right? I could even state here that all we would do is just simply calculate A plus B plus C plus D, right? We just add the 4 numbers together, and then remember to compute the average. You just divide by however many numbers you have, which in this case would be 4. Okay, perfect. So now we have a different question. It's related to this idea of computing an average. Here's what we have. Now suppose that I wanted to compute the average y value for a function. Okay. Well, using the previous idea, that is, adding up all the values and dividing by how many you have, would really start to become difficult. Because if I was to just go ahead down here and maybe say just picture a function really quickly, right? If I was to draw out, well, that line's kind of slanted, but if I was to draw out here a function, right, that maybe, say, starts like this, who knows, maybe it goes like this, right? And I say, all right, so here's the interval from A to B, and I first want you to find all of the y values on the function, all of them. So you have to imagine every single possible point on the entire function, grab all those y values and add them all together, and then divide by how many there are. Well, the reason that that's difficult is because how many y values are on this function? I mean, infinitely many. There's infinitely many points, right? So every single point has its own y value that's on the function. So how in the world can I ever possibly do this? I can't grab every single possible y value. So we're going to need a different approach. So here's what we're going to go ahead and try to do here to help try to address this very, very important question. First off, let's suppose that, kind of like what I've sketched over at the right, that we have a continuous function that we'll call f of x on the interval from a over to b. Okay, so here's my function f of x, and it's sketched out on the interval from a to b. It's nice and continuous. So if I wanted to find my average y value, again, that's going to be, there's some value on here that's going to end up being the average. I don't know, maybe it falls, say, like right here, right? So like I could see that right here, maybe this is, say, the average height of the curve, right? I have no idea if this is where it would be, but let's suppose that this right here, that's my average y value. Okay, so if that is my average y value, how would I find that that's the average? Well, to start, what I would do is something that we've actually done every time we've dealt with a Riemann sum. We're going to start by taking the interval from a to b and chopping it up into smaller subintervals. So I'll state here that we begin by dividing up a to b into n equally spaced or equally sized subintervals. Okay, so each of these then would have our standard width. So each with a width of delta x, which of course we know how to calculate delta x. We would say calculate the length of my interval, divide by however many of these intervals I'm going to create. So I could start to imagine kind of where these would occur. Maybe I would have an interval that looks like this, and maybe like this, right? And maybe like this. And I'm just making each of these kind of equally sized all the way along the way, right? I could have a whole bunch of them. Doesn't matter how many I have, but I could imagine kind of creating all these kind of equally sized little intervals along here. Now, once I've done this, I'm going to go ahead and I'm going to kind of choose to look at each interval one at a time. And I'm going to say, gosh, on this interval there are still a ton of y values. So if I'm interested in calculating the average y, how about what I do is I have kind of each interval pick out a representative y value to kind of say this y value represents the y values in this interval, and we'll kind of send that forward as a representative to help try to calculate an average. So I'll word that in the following way. So I'll say, if we choose a sample point, which we'll call xi star, from each interval, then we can attempt to approximate the average y value. Average y value. Okay, let's see how this is going to work. So I'm going to take, going to each interval, I'm going to go ahead and grab out of here some point that then I could go up to the function with and grab a y value. I'm again going to do that on every single interval. Okay, it doesn't matter again where I'm selecting this x value to be inside the interval. I could literally just grab any point, and then I'm imagining I'm going to go up or down until I hit the function. And you can see here I'm filling in all these kind of green dots that are going to be on my function, all these different points that are on here. Okay. Now as I do this, what I'm doing is I'm creating a whole bunch of different possible y values that would need to be used to calculate the average. Each of these, again, remember, is coming from selecting an xi star in each interval. So as I do this, I'm grabbing a bunch of different y's, and I could imagine then that while these aren't all the y's on the function, these are going to be some of the y values on the function, and so I could go ahead and use these to try to estimate what the average is. So I could do that by doing the following. I could say that the average y value could be approximated by saying, let's take the function, and how about we plug in x number 1 star, and then add in the y value for x number 2 star, and I would just keep going and going and going all the way down until I hit x number n star. So that's like the very, very last one down here. So I add up all of the green y values that I have, and then I know that since I made n intervals, I have n y values, and so I divide by n. And obviously, again, this is not going to be the average of all the y's. It's just an average of some of the y's. Okay, so let's go ahead and see what we might be able to do with this after we have this set up. Well, one thing that I'm going to note right here is that since we stated that delta x was going to be equal to b minus a over n, then there's absolutely nothing wrong with doing a little bit of algebra here. I could multiply both sides by n. That would get n times delta x is equal to b minus a. And then I could actually divide by delta x and get the following. I could get n is equal to b minus a over delta x. So again, if I multiply n over and then divide back over the delta x, I can end up with a statement like this. Now, the interesting part with doing this is that I can see that n is occurring here inside this average formula. And if we use this equation here, n equals b minus a over delta x, in the calculation above, we would end up with the following. I would be able to say that my f of x1 star plus f of x2 star, that went all the way up to f of xn star, that was all over n, could now be replaced with f of x1 star plus f of x2 star all the way up to f of xn star. But now, of course, it could be divided by what n is equivalent to, which is b minus a over this value of delta x. Now, of course, if I wanted to, I could choose, since I'm dividing here by a fraction, to instead multiply by the reciprocal. If I was to do this, notice that I would still have, again, all of my f's added in the numerator. But then I would end up having to multiply that gigantic sum by delta x, and I could imagine then it would then be divided by this b minus a. So notice I've just multiplied by the reciprocal of my fraction here. But there's a couple other things that I can do here. What if I was to go ahead and take everything on the top of this fraction and kind of pull it down off to the side? That is, I rewrote this as 1 over b minus a, and then multiplied by my giant set of brackets times the delta x. Or maybe even better yet, what if I did this and also distributed this value of delta x? So notice that each one of my special y values now got multiplied by this value of delta x. So I would have something that looks like this. This goes all the way up to f of xn star times delta x. Well, if I wanted to, since this is one gigantic sum, I could actually rewrite that much more easily using summation notation. I could say, really, all I'm doing here every single time is changing the number on the x. The number starts at 1 and it stops at n. And so I really just have f of xi star times delta x. You might start to see something familiar shaping up here. Now, here's what's interesting. This right now is a formula that computes for us this sort of partial average value. The issue right now is that we haven't used all of the y values on the graph like we were supposed to. But notice that if n was to increase, instead of n giving us, I don't know how many intervals this is, but let's say it's close to 10. So instead of 10 intervals, what if I had 10 million intervals? Then I would have 10 million of the y values on the graph. And while that's still not all of them, it's a heck of a lot better than only using 10. So I could see here that as the value of n continues to increase, my average is going to be incorporating more and more points, getting me closer to the actual average. So we would expect then the following. We would expect that as n increases, our approximation improves, and so we would state that the average value for the function would be equivalent to, how about we take a limit and we apply it to everything that we had in this average value calculation. So I would just say, how about instead of using just n intervals, I go ahead and I actually let that number of intervals go off to infinity. Now, one final cool thing that I can actually do here is that I can see that, wait, 1 over b minus a, that's just going to be a number. And so I can take that number and actually pull it outside of this limit. So that's 1 over b minus a. And then I would be left with a limit as n approaches infinity of this sum as I goes from 1 to n, f of xi star times delta x. And you might notice something even more incredible. What does this limit actually represent? Well, we should be able to see that this here represents a definite integral. How awesome is that? There's a definite integral sitting right there. This is really, really, really surprising. How in the world did it come out to be the fact that there would be a definite integral sitting right here? If I was to go ahead then and think about summarizing this in one final way, I could state exactly what's down here in the box below. The average value of a function, the average y value of the function, is actually the same as 1 over b minus a times, and I could represent all of this as a definite integral. Now, just pause for a moment to think about just how unbelievably weird this is. You have to feel this because you're trained for so many years in math classes to just read something in a box and go, okay, yeah, I guess if you say so. But then you lose all of the beauty of the subject. This is almost completely counterintuitive. Notice what we said. You could find the average height of a function by finding the area under the curve and then multiplying by 1 over, what, b minus a would be the length of the interval. Oh, so if you want to find the average y value, very obvious. Find the area under the curve and then just divide by the length of the interval. What? That's so weird. How does that make sense intuitively? It really doesn't make much sense intuitively. But we can see here that we have a carefully developed argument to show that is what we end up with. So this fact here is extremely important. It's extremely important. It's how we define what we would call the average value of a function. Notice here that we use this little f with the subscript avg, so f average. That's still standing for that average y value of the function. Now in the videos to come, we'll take a look at some examples where we'll try to practice utilizing this idea and finding average values of some functions. But for the moment, you should pause and be amazed at the fact that somehow, the area under a curve was linked to finding the average height. How weird is that?